Dr. Rico here. This is a lecture from my course, System Dynamics. The syllabus link is in the description. All right, so today we're going to do a complex Fourier series example. All right, let's do it. There are several flavors of Fourier series problem: trigonometric or exponential, analysis or synthesis, plotting partial sums, plotting spectra, etc. Of course, problems just present us an opportunity to traverse part of the landscape, to mix two metaphors like 31 similes. If you're old and like ice cream, you'll know that reference. All right, so on to the example. Here we are. Consider a rectified sinusoid. You may recall from when we looked at sinusoidal electronic signals that sometimes we wanted to go from an AC or sinusoidal signal to a DC signal. The first thing that we did was we rectified the negative part of the signal to make it positive. Okay, so that's what we're doing here. We're going to look at a mathematical version of that sort of signal, ignoring any sort of losses that come about from that process, or any voltage drops. So we're looking at it in a sort of idealized environment, or just think of it as being just this function of time, f of t, the absolute value of a cosine omega t, where a is an amplitude, omega is the angular frequency, t is time, as shown in this figure. So in figure FS example .1, the function is plotted over several periods. So we see if we use dimensionless time here, we will multiply omega and t, which is just the argument of cosine here. Take the absolute value. The peaks occur at a, so that is what this function looks like. The fundamental period is, instead of the usual 2 pi over omega, it's pi over omega, because this sinusoid gets sort of chopped in half and repeats exactly what would typically be the negative part of the cosine becomes positive, and therefore the period is actually, the fundamental period is actually half what it typically would be for a sinusoid with frequency omega. So we get pi over omega, half the unrectified period. We're going to do 3 different parts for this problem. Part A, perform a complex Fourier analysis on the function of time, computing the complex Fourier components c plus or minus n. So when we do the complex form of the Fourier series analysis, we compute the components. We usually call them c, and we usually use plus n for the positive harmonics and minus n for the negative harmonics. Okay. Part B, compute and plot the magnitude and phase spectra. Okay, so we have a complex component Fourier series. We need to compute what the spectra are from that complex representation. And finally, we'll convert the complex components into trigonometric components an and bn, corresponding to the cosine and sine trigonometric functions. So that form of the Fourier series is also valid, of course, and you can convert between the two. So we'll do that in the last part of this problem, part C. So let's begin. Part A, complex Fourier analysis. All right. The complex Fourier analysis, which we defined in definition 9.2 of a previous lecture, will be applied in a moment. However, it is convenient to first convert f into an exponential. We can write f over a single period, negative big T the period over 2 to big T over 2, as the absolute value of a cosine omega t equals the absolute value of a times the absolute value of cosine omega t, which is just a property of the absolute value. Furthermore, we remember that cosine omega t over this period, negative t over 2 to t over 2, looking back up here, from negative t over 2, that's this, to this, cosine omega t is already positive, okay? So for that entire period, it is positive. period, remember, of the absolute value function. So we can drop the absolute value as long as we're careful, recognizing that we've restricted our time to being during that period. And finally, we can use Euler's formula that converts a cosine into an exponential, absolute value a over 2 times e to the j omega t plus e to the negative j omega t. Great. So we've converted this sinusoid into a complex exponential, or an exponential form. This is going to be convenient because we're going to, in a moment, apply the complex Fourier series analysis equation, and that includes exponentials as well. It's nice when we have exponentials with exponentials and trigonometric functions with trigonometric functions. So let's do it. Applying a Fourier analysis a la definition 9.2, the definition of the complex Fourier analysis introduced previously, with harmonic frequency omega n being 2 pi n over t. N here is the harmonic, right? That's going to be one of the variables here. So for each harmonic, there will be a component c plus n and a c minus n, okay? And if we just simply substitute in f of t with the expression that we just derived above for it here, we will be able to, so just connect that right up here, plug that in for f of t, and we will be able to combine this term. There are a lot of steps in this simplification process that I thought it would be worthwhile for us to just see and talk about, but not necessarily write down all of, because I want to keep this as compact as possible. But it's important to look at all of these steps and understand how to do this. Let's go ahead and plug in this function of time. We see immediately that we can bring constants out of the integral. So absolute value of a, the 1/2, bring them out here. And it's not terribly ugly looking at this point, but let's go ahead and combine the exponentials. Remember, when you multiply two exponentials, you add their exponents. So that's what we'll do. And you get these two exponentials. Now, actually taking the integral as we need to do, so we can integrate each of these terms separately, of course, and sum their integrals. Each of these integrals separately is just an exponential. You pick up a denominator for your fraction here from that antiderivative. It's a definite integral, so we evaluate over that period. So we choose the period from negative t over 2 to t over 2, and substituting in big T over 2 and subtracting the negative t over 2 result, we get 4 terms here that show up. And notice we're trying to simplify now that we've evaluated the integral. We would like to simplify this down as much as possible. And we notice that the way that it naturally came about, we have mixed terms. We have omega minus omega n in the exponent here, and omega plus omega n in the exponent here. So the first two have mixed frequencies, okay? And those mixed frequencies don't combine very easily. So what we do instead is, when we notice that the bottom here, the third and fourth terms have mixed frequencies as well. So we just swap them, okay? So we're going to swap them around so that we get the omega minus omega n frequencies in this term and the omega plus omega n frequencies in this term. This also allows you to factor out the fraction associated with each of them. So we do that here. We're getting somewhere. This might, and hopefully it's starting to look familiar to you, it looks like the Euler's formula associated with the sine function. So if we just apply that Euler's formula sort of in reverse here, if you will, which is to say going from the exponential form to the sinusoid form. We have to pull in this j and this 2 from the exterior of each term. We get this term turning into this sinusoid, and we get this term turning into this sinusoid. We can simplify it further if we substitute in that big T, the period, is pi over omega, and omega n, which is the harmonic frequency, is 2 pi n over big T, where if you substitute in big T into this expression, you get that omega n is just 2n omega. So the harmonic frequencies are multiples of the frequency of the sinusoid, the absolute value of which we took as part of the problem, right? Cosine of omega t. So this simplifies to c plus or minus n equals the absolute value of a over pi 1 minus 2n sine 1 minus 2n pi over 2 plus absolute value of a over pi 1 plus 2n sine 1 plus 2n pi over 2. Okay, so that is certainly simpler than we had before. Notice that it is only a function of a and n, okay? Using a product to sum trigonometric identity from the trigonometry appendix, if you go there in the notes, this further simplifies to the following expression. So we can combine the two sine terms into a single cosine of pi n, and we have this remaining factor here, which for n odd or even, so if n is odd, notice that cosine, so odd would be 1, 3, etc. So cosine of pi, for instance, is -1. Cosine of 3 pi is also -1. If it's even, then, so 0 is even, so cosine of 0 is +1. Cosine of 2 pi, also even, is 1, etc. So they're positive. You get a positive sign if n is even. You get a negative sign if n is odd. And the negative sign when n is odd cancels this negative sign, if you will. And we get this when n is odd and this when n is even. Okay, this is a nice compact form for our complex Fourier components. All right, so good. Alternatively, so that was actually, I mean, I worked it out by hand. It took a while to do it by hand. And I like showing you these computing tools that help you do this even quicker. So here is that. We could use Matlab's symbolic math toolbox rather straightforwardly. Declare some symbolic variables that are all going to be real for now. We're going to refine that assumption a little bit later on, but for now we'll start out with them all being real. Now define the function of time f and the known relations in a dictionary. So function of f, we're going to put the absolute value of a times cosine omega t. We're only going to work with this over that period from negative t over 2 to positive t over 2 because we want to be able to simplify this without any issues using Matlab symbolic toolbox. And if you just put an absolute value around the cosine, it's gonna cause trouble in simplifying this, even though it would be nice if we could do that because it would help us be confident that we're not making any mistakes. We have to restrict our domain though. We have to remember that. We'll also define this variable props. Okay, so props is going to be a dictionary of the different properties. T is the period and Wn is going to be omega n. So we just give these two what will later become substitution rules for us in the symbolic analysis. So apply the same Fourier analysis as before. This is the integration that we did before. We plugged in f, integrate from negative t over 2 to positive t over 2. Remember, that's okay if we don't have the absolute value on the cosine, as long as that's our integration domain. So if you have Matlab do this symbolic integration and simplify the result, substituting in the different properties that we talked about a moment ago, this is the result. Actually, the same result as before, or by hand. That's good news. Sometimes a symbolic solver like this will happily do the integration, but give you a very challenging expression to look at. Using functions like simplify sometimes helps, but it doesn't always help. So this is a nice one, though. It actually does turn out to be a pretty nice little expression. And we can even check the odd and even assumptions. So you can use this assume function in Matlab. And this is how you tell it to assume n is odd. Okay, you say assume n is odd. We assumed it was real before, and we're going to simplify it with that assumption and print it out. And this is what comes out, which is the expression that we got for n being odd before. And if we then clear our assumptions using this syntax, we can assume now that n is even, which is saying that if you divide it by 2 and that is an integer, then it must be even. And we simplify. Again, we get the version that we looked at before when we assumed that n was even. So odd and even, great, everything's working. We're going to clear our assumptions on n before we go on, and we're going to assume it's real. That's just so that we have expressions later on that don't make that integer assumption of n for us before we want to. So we want to see what the result would be for any n, and then we're going to look at it when n is an integer. So that's the idea there of assuming n is real for now, and later assuming it's an integer. It's fine if you assume it's an integer the whole time. So now we're going to move on to part B, the harmonic, amplitude, and phase. And don't forget, with spectra, we're going to plot the spectra here, the amplitude and phase spectra. So according to, again, the lecture where we define the Fourier series, the harmonic amplitude is, in terms of the complex components, 2 square root Cn times C minus n, which if we substitute in, Cn and C minus n are very similar. A place you could get into trouble here is if you don't remember that when you take the square root of something squared, what comes out is actually the absolute value of whatever that was that you squared, right? Sometimes we forget that. It's good to remember that. So that's where we got these absolute value terms showing up. Okay, we picked up a factor of 4 in the numerator, another factor of 2, and that's a good expression for the harmonic amplitude. Let's check with Matlab because we've got it all queued up. So let's assume n is real. I just did this to make sure that we remembered that this is our assumption on n. We look at Cn and we simplify it with, so we just plug in the expression from above. Now we're going to substitute in, because we didn't differentiate between Cn and C minus n in our previous expressions, we're going to be able to reuse Cn and substitute in 4n minus n to get C minus n. So we multiply Cn and C minus n, take the square root, multiply by 2, and the result is here, which is what we wrote above from our analytic approach. And if we assume n is an integer, it gets even simpler because cosine then allows us to simplify. So we get this nice expression for Cn, even simpler than we had before because we didn't make that last step in our by hand calculation. So symbolic toolbox really coming through for us here. All right. Plotting the harmonic amplitude is pretty straightforward. We know how to plot things in Matlab. But first, we'll make Cn something, the harmonic amplitudes, into something that can be numerically evaluated, and we choose parameters accordingly. So we're going to set a, the only other parameter that shows up here is a. We'll say p dot a is equal to 1. We'll substitute in to Cn this parameter a. There's only one. If there were more parameters, we could do the same syntax, but have other p dot other parameters listed above. And we use this Matlab function, in order to take a symbolic expression and express it in terms of a numerically evaluable function. So Cn fun, if you give it a numerical value as an argument, it will return what Cn is numerically. So let's do the plot now. We do -10, so harmonics down to -10 in frequency and up to +10. These are actually in harmonic number. If we wanted to, we can convert that to an actual frequency. So it would be omega sub n instead of just n, the harmonic number. So we decided to just plot by harmonic number. Kind of up to you. But remember, this is a frequency, right? These correspond to frequencies. So we're in the frequency domain here, plotting in the frequency domain. The harmonic amplitudes here. We say that we're doing Cn divided by the absolute value of A because if we set A equal to 1, as we did, the way that it enters into our expression, if we go back up here, we see that the absolute value of A shows up in the numerator. So setting A equal to 1 or plotting something over absolute value of A is equivalent. So it's a little bit more general to say it's Cn divided by the absolute value of A. And we just evaluate Cn at these different values and plot it. We use the stem function for a stem plot here. We plugged in our array of harmonic numbers here. And this function, another nice thing about the Matlab function is that it gives you an ability to vectorize your function as well. So if you give it a vector of values or a matrix of values, it will apply that function to the different elements of that matrix. So it's a pretty nice function, this Matlab function. So here's the result, and we see that there's a very strong component at 0 frequency, or the 0th harmonic. Sometimes we call this the DC value, or the DC frequency. And it just corresponds to 0 radians per second. And we have a component at 1, the first harmonic. This is the fundamental frequency. The second harmonic, the third, fourth, and it's trailing off, right? This is dropping down to 0. If you look back at this functional form, here it is in MATLAB sort of form, but if we wrote it out like this, it would be 4 absolute value of A over pi times the absolute value of 4n squared minus 1. So we see this tailing off that happens pretty quickly here as we increase n plus or minus. It should be symmetrical. This is going to be an even function because we have that square there on n. The only way n enters is through a squaring. So it'll be even. And we see that we have this tailing off that happens pretty rapidly. So mostly we have a DC component. We have a we have the fundamental frequency comes in pretty strong, and then everything else is pretty small. We have a little bit of a second harmonic, but for the most part it's gone by that point. So the magnitude is actually kind of what we would expect, right? Because we took a cosine and we just took the absolute value of it. So we're not gonna get back a pure cosine. A pure cosine would show up at its fundamental frequency and nowhere else. We do this absolute value, we get this big DC offset. This is why when we do AC to DC conversion, the main operation is to rectify the signal, right? At negative interval and make it positive during that interval. And the net effect of that is to have this significant DC offset to the function. So that's the main difference between the cosine function and the absolute value of the cosine function, is that we get this large DC component. There are also some higher frequency components, but they're not very significant. So relative to the DC and the fundamental components. All right, so that's the harmonic amplitude spectrum. Now let's move on. Let's find the phase a la equation series .12 with Matlab directly. So the phase spectrum is easy to compute from the imaginary and real components. Arctan2 keeps us in the quadrant, the correct quadrant. That's why we use arctan2 instead of arctangent. Simplify it. The expression given here is a little hard to parse. We're seeing this function show up here, sine, okay? Sine, S-I-G-N, not S-I-N or S-I-N-E, sine with a G just gives you back the sign of the argument that you give it. So if you give it -5, it'll give you -1 back. If you give it +5, it'll give you 1 back. If you give it +10, it'll give you 1 back. If you give it -12, it'll give you -1 back. Just returns the sign in the form of +1 or -1 of the expression that you give it. So most of this comes down to computing the sign, okay, +1, -1. And what you can see if you really dig down into this expression and really try to parse it, it takes a little while, but there are only two possible values that can arise here, 0 and pi, all right? These are the two possible values of, what are we computing? It's the phase of the complex Fourier series components, okay? So this is our phase spectrum that we're computing here. We can plot the phase similarly to how we plotted the amplitude. First, we're going to make a numerically evaluable function, just as before. We substitute in a equals 1, just as before. So let's see what the plot looks like. And we get this. So it's mostly switching off between 0 and, what is this? That looks like pi, right? Pi. 0, pi, depending on if n is odd or even, 0 and pi. It's a little bit more subtle than that because when n is 0, we also get 0, so it's not perfectly odd, even, but it's close to that, right? So we switch off in phase between 0 and pi, just like we saw from our functional form. And we're ready for part C now, conversion to trig form, okay? According to the definition from the Fourier series lecture, the trigonometric components can be computed from the complex components as follows. So we just take for an, we just say that it's equal to C positive n plus C negative n. And for Bn, we say that it is equal to JCn minus C minus n. Okay? We're now fully just using Matlab's symbolics toolbox because it's really working for us in this problem, right? It's not giving us crappy results, giving us nice results that are pretty simple. Doesn't always happen, depending on the problem you're working with. But in this case, it's working well for us. So we're gonna go with it. AN comes out to be this, which looks a lot like our CNs, right? BN is 0. It's always 0, okay? The fact that BN is 0 shouldn't surprise us, though, because f of t is even, after all. So if you go way back up, if we go all the way back up to this graph of f of t, we see that f of t is even, and we know that if we compute the trigonometric Fourier components of an even function, the components of sine, S-I-N-E, sine, end up being 0. Those are the BNs, okay? And our ANs, the components of cosine, the even function, will be non-zero, or at least some of them will be. So that is how to compute the complex Fourier components of this function, how to calculate and plot the magnitude and phase spectra therefrom, and to convert the complex components into trigonometric components for the trigonometric Fourier series that is the alternative version to what we used in this lecture. So I hope you enjoyed this example. Tune in next time for some more Fourier. Catch you later.